Let me just mention that the term contextual analysis is a bit too general probably for this talk. Perhaps a better term would have been contextuality analysis, and the term contextuality is used in a special technical meaning. It is an interdisciplinary area of research that spans primarily quantum physics, behavioral sciences, and computer science. So another way of looking at it, the way that I would, my preferred way of looking at it, it's an abstract mathematical discipline with applications in quantum physics, computer science, and behavioral sciences. So I will use several examples throughout the talk, and they would mostly be from quantum physics, and not because there is a special reason for this, but historically, this type of analysis actually was born within the foundations of quantum physics. And then in parallel, it was also developed in psychology in the context of so-called selective influences, something that I have contributed quite a bit to. And then, at some point it became obvious that the two mathematical apparatuses are essentially identical. And so this more general mathematical discipline was born. So let me mention let me just give you a brief overview of what I'm going to talk about. Well, the reason that it has such broad area of applicability, this discipline, is that it applies to anything that can be described by systems of random variables, and that's virtually everything that you can think of. And so I will introduce the concept, and I will explain what are contents and what are contexts, and what are stochastic relations among the random variables. Then I will talk about the main mathematical tool that we're using in contextuality analysis. And this is the notion of a probabilistic coupling. It is being used primarily, or the way to look at it, at least within the framework of this talk, is that it is a tool for measuring differences between two random variables taken in isolation or taken within a system. And, in fact, I can already tell you that essentially the difference between these two differences, the difference between the differences of two random variables when taken in isolation and when taken within a system is what contextuality is about. Then I will briefly mention measures of contextuality and non-contextuality. It is a very, it's a relatively new and very rapidly developing sub-area of contextuality analysis. And then I will talk about epistemic or Bayesian random variables, which is a kind of a better term than probabilities. Random variables with applications to such, I just chose these applications, the Liar's paradox, Escher's lithograph, and Penrose's on Penrose type impossible figures. And finally, time permitting, and kind of in order to make it a bit more entertaining, I will talk about so-called free will theorem that was recently proved and promoted by Conway and Cochin. So let me proceed. This is an example of a system of random variables. So we call it a system because it is a set with a certain structure. So it is a set of random variables that are classified in two ways. They're classified according to what question they are answering or what measurements they are the outcomes of. So for example, these two random variables answering one and the same question, Q1, These two are answering the same question. These three are answering the same question, and so on. And then they are also grouped with respect to their contexts. So C1, C2, and so on are contexts, and they are represented by superscripts, whereas the contents, the questions they are answering, are represented by subscripts. So within a context, the random variables are measured together in some well-defined empirical sense, for example, simultaneously or in a succession. But the important thing is that the values of these three random variables, for example, in the first context, they come in triples. So you can have a table of triples, and you know, if you have a long enough table, then you will be able to speak about such things as assessment of the correlations between them, you know, the probabilities with which this one can be equal to this one, and so on and so forth. You cannot do the same thing, and this is a critical point. You cannot do the same thing across the context. For example, these two random variables that answer the same question, but they are in different contexts, they never co-occur together because different contexts are mutually exclusive. If you are using one context, you are not using the other one. And it means that these two random variables never come in pairs. So if you have a list of values of this random variable and list of values of another random variable, you will not know which value to pair with which value, right? So there is no pairing scheme. And as a result, there is no joint distribution. It is a very simple fact, but sometimes it comes as a surprise to many people because there is some kind of strange belief that in theory of probability, any two random variables are jointly distributed, and you know, which is obviously not true for reasons that I've just mentioned. Mathematically, a random variable, just to mention it, but I'm not going to pursue the very rigorous kind of mathematical analysis of random variables in this talk. But mathematical random variable is a measurable function from one probability space to another, or to a measure space. And so mathematically, the random variables within a given context are defined on the same domain probability space, but the domain probability space are different across the context. In different contexts, we have different domain probability spaces. As a result, no joint distribution. Okay, so this is the empirical situation that actually started the theory of contextuality, even though at that time it was not known by that name. The term contextuality was coined a bit later, but this is so-called Einstein-Podolsky-Rosen/Bohm system, or B can also stand for Bell rather than for Bohm. And this was the system that was provided the first clear demonstration of what we now call contextuality. So let me just explain it very briefly. You have two particles and they are separated by light years. So, you know, any kind of interaction between the two is precluded. Alice is measuring this particle and Bob is measuring this particle. And each of them can choose one of the two axes. So Alice can choose 1 or 3, and Bob can choose 2 or 4. And they measure so-called spin along this axis. And assuming that it is something like an electron or spin 1/2 particle, each spin can have two possible values that can sometimes be referred to as up or down. So the questions here, Q1, Q2, Q3, Q4, are the questions, is the spin along axis 1, 2, 3, 4 up or not, right? So, and so the value of this random variable is yes or no. So it's up or down, right? And when Alice chooses, let's say, in axis 1, then Bob can choose 2 or 4. And as a result, you know, you have two contexts. One context is Alice measuring spin along axis 1, and Bob chooses axis 2. And in another case, It is again access 1 for Alice, but now Bob chooses access 4, so it will be another context, right? And because the interaction between the two particles is precluded by special relativity laws, the probability distribution of this random variable is exactly the same as of this random variable. In other words, what the probability with which the answer to the question is the spin along axis 1 up, the probability that the answer is yes is one and the same probability irrespective of which axis is being chosen by Bob. There is no interaction between the two, and vice versa, obviously. So we have the same distribution in this column, the same distribution in this column, the same distribution here and here. This is so-called cyclic system of rank 4 in the terminology that we are using with my colleagues. And in this case, we have so-called consistently connected system because the probability distributions are the same within columns, right? So one might be tempted in a situation like this to say, well, you know, since the distribution is the same along axis 1, then Alice couldn't care less whether Bob is measuring anything at all. And as a result, these two random variables can simply be considered as different realizations of the same random variable. So why not simply drop the superscript here and say it is R1 and it is also R1, right? Or analogously here. So just consider these two the same, these two the same, and so on and so forth. And as it turns out, when you do that, you run into a contradiction, a mathematical contradiction. And this mathematical contradiction shows to you, proves by reductio ad absurdum, that the assumption that it is the same random variable in each column is wrong. So you have to distinguish them even though their distributions are exactly the same, right? So it is the first and a simple case of contextuality. And I will explain it in a bit greater detail in a moment. Just to give you just another example, again, taken from physics, but it's a very different example. It doesn't have to be the situation in which, you know, the two things are separated by light years or anything like that. You can have a single particle. There are 5 axes here, and they can be measured 2 at a time. And the two can be that can be measured together are connected by edges of this pentagram here. Right, so you can measure, for example, 2 and 3 together and 2 and 4 together. Yeah, no, sorry, 2 and 3 together and 2 and 1 together, right? These are the, and again, you get these pairs. This would be cyclic system of rank 5. And again, this is something where you can show that even though the distributions by the laws of quantum physics now, the distributions within the columns are the same, we have a contradiction resulting from simply identifying these random variables within a given column as the same random variable. Okay, I will just mention briefly also that, you know, from these two examples, you might have the impression that context can be defined by the set of contents that enter this context, right? So here in first context, you have 1 and 2 questions. In the second, you have 2 and 3 and so on. So they are all different, but it doesn't have to be the case. For example, this is a very important, even though arguably the simplest possible system where contextuality can be obtained. And you can see that the same questions, Q1 and Q2, enter both contexts. But it's simply something changes here. For example, the 2 questions can be answered, can be asked in one order in C1 and in the opposite order in C2, right? So and here is analogous situation for 3 questions in 3 contexts. So the sets of contents represented in a context is not unique for a context. Okay, so let's consider now a non-physical example, kind of an example that actually could be a realistic example if you actually ask these questions. So suppose that you are asking someone, whether this person is contemplating an overseas trip this summer. This will be your Q1 question. And the second question that you would ask of the same person would be whether he is afraid of traveling, during the pandemic, right? So let's say you ask these questions, and let's say in one case you are asking from one person, you are asking the questions in this order, first about the trip and then about the coronavirus. And in the second case, you are asking them in the opposite order. Well, the empirical fact, this is a very well, investigated empirical situation in psychology and sociology, and it is well known that the joint distribution in this first context is different from the joint distribution in the second context. Now, I'm going to illustrate the notion of contextuality on a toy example that's completely unrealistic. And this would be the example in which I would assume that the probability of answering yes or no, denoted here +1, -1, that the probability is always 1/2 for all questions and in both contexts, right? So if you're asking about the overseas trip, probability of yes is 1/2. If you're asking about coronavirus, the probability of yes is 1/2. And the same is true when you're asking these questions in the opposite order. If this happens, then you can argue in the following way. You can just look at only at the question about the overseas trip and ignore the other question. In other words, you are ignoring the context now. You are just looking at the two random variables in isolation. And you are saying, well, they are identically distributed here and here, the same distribution. So why not to consider it as simply one random variable, right? With uniform distribution, 1/2, 1/2. Let's say you agreed that you would do that. And then you look at the second random variable, notice that it's also distributed in the same way in both contexts, and say, well, why wouldn't I consider them, these two random variables are the same random variable, R2, right? So I dropped the superscripts. I forgot about the context. But now if I continue to entertain this possibility that these two random variables are one and the same, and these two random variables are one and the same, then their joint distribution also has to be the same, right? It is one pair of random variables. And let's say that empirically you find out that it is not the case, that in one case, let's say, here they are perfectly anti-correlated. So if you say yes to one, you say no to the other. Let's assume that. And in the other case, let's say you find out that they are independent. So all joint probabilities here is 1/4, right? Let's say it is the case. Well, then you run into a contradiction, right? So you assume that it is the same random variable, but you get two different joint distributions. And as a result, you have to conclude that the assumption that these two are equal to each other and these two are equal, well, actually, I take it back, that these two are different realizations of the same random variable, and these two are different realization of the same random variable, that this assumption is wrong. So they have to be different in spite of the fact that taken in isolation, they can be identified, right? So another way of looking at it that would be useful for getting the general definition of contextuality is that when you consider them in context, then the contexts force them to be more dissimilar than they are if they are taken in isolation. So in this case, of course, when they are taken in isolation, they are not dissimilar at all. They can be identified. But when taken within the context, they have to be different. So this added difference, kind of forced difference by contexts, is what forms the intuition behind the general definition of contextuality. So I have already mentioned to you that it's exactly the same type of reasoning, just mathematically a bit more complex, that leads you to a contradiction in the case of EPR-Bohm system of random variables. So let us now make my example realistic. Well, obviously, you can easily imagine that if I ask you about an overseas trip, and then I'm asking you about coronavirus, then your response to the first question can be, let's say, enthusiastically yes. But if I'm asking you in the opposite order, so I first reminded you about coronavirus and then ask you about the overseas trip, then maybe the probability with which you would say yes now would be lower than in the first case, right? So it is actually a well-documented fact that the individual probabilities here will be different for the answers to the first question, answers to the second question. This is well documented even for less dramatic questions than, you know, coronavirus or anything. Just very, very simple general knowledge questions. You know, the probability of answering yes to one of them depends on whether it is asked first or second, right? So it is just an empirical fact. So we have so-called inconsistent connectedness. In physics, this is also called disturbance, which is a form of context dependence. And so we can say that this random variable and this random variables in different contexts, they are different random variables. So because they are now differently distributed. And this obviously is a form of context dependence, but it is not contextuality yet. So contextuality is a special form of context dependence that I'm going to explain now in a moment. But first, just to mention that we also have the situations with inconsistent connectedness when you have, for example, 3 measurements performed 2 at a time in time, right? So it means that they are following each other in time. This horizontal axis here is time. So you can ask questions 1, 2, or 1, 3, or 2, 3 in this order. And obviously, if 2 is asked after 1, it can be influenced by 1. And if 2 is asked first and 3 after that, then 2 is not influenced by anything. So it's called signaling in time in physics. And you know, it is a form of disturbance that actually is being also investigated you know, quite intensively. Here is something that you know, all of us know from popular literature: two-slit experiment in quantum physics, right? And physicists usually present this as a very puzzling kind of very counterintuitive empirical situation. And in this situation, if you analyze it contextually, then you will be able to present it by this cyclic system of rank 4, and find out that it's inconsistently connected. But you know, even though I'm not going to talk about it, it's kind of interesting that it's not contextual system. So there is no contextuality involved here. In that sense, it is less interesting system than, let's say, that EPR bomb system or anything that I mentioned previously. Even this 2-question system exhibits more contextuality than this. So so let's talk now about this simple 2-question paradigm. But this time we will allow for the distributions to be different, you know, along the columns of this matrix. So let's consider now R1 and R2. I know that they are different now. They are different random variables. But let me ask the question how different they are. So how would you answer the question how different are 2 different random variables? Well, one way of answering this question is this. We know that they are not jointly distributed. But let's say I replace R with its probabilistic copy, and R2, I will, and this R super 2, I will replace with its probabilistic copy and make them jointly distributed. So in other words, well, first of all, notice that they are differently distributed in the sense that in one situation, the probability of yes is Q, and in another situation, the probability of yes is P. So now let me replace them with their probabilistic copies, but assume now that these copies are jointly distributed. This is, in fact, what probabilistic coupling is. It is a probabilistic copy of several random variables that is such that in this copy, all random variables are jointly distributed in some way, unspecified way. So you are saying, well, you know, these two random variables are such that the first one, the red one, is distributed as this one, the red one here, and the second one is distributed as this one, but now they are jointly distributed, right? And I will ask you, because they are jointly distributed, I'll ask you, among all possible joint distributions of these two random variables, which one would provide the greatest coincidence of these random variables, the greatest probability with which they will be equal to each other? Or if you wish, the smallest probability with which they will differ, right? And this will be a measure of difference between the two random variables, right? The if the probability with which they can be different from each other is very large, then they are very different random variables. If the probability with which the minimal probability with which they can be different, can be made different, is very small, then they are close to each other. And it is easy to prove, by the way, that if they are identically distributed, then you can always have the joint distribution here such that they will be equal to each other with probability 1. In other words, they will not be different at all, right? In this, from this point of view. So we consider all possible joint distributions, and there is a simple theorem that says that this joint distribution, this matrix will provide for so-called maximal coupling, meaning that it will be the smallest probability with which they are made different. And this is the probability with which this smallest probability with which they are different actually happens to be just the absolute value of the difference of these two probabilities of saying yes, right? So P minus Q in absolute value is this difference. Well, maybe some of you know this concept, but there is a general concept of comparing two probability measures that's called total variation distance. And this actually is a total variation distance in the case of binary random variables, right? So we have total variation distance between the two original random variables is being presented as as the probability with which in the coupling the two random variables are different. Okay, and you can do obviously the same thing for the second pair of random variables, so for these two, and again their difference will be the total variation distance between them, right? And now we come to the critical point. Now let me consider the overall coupling of all these four random variables. Overall coupling is here, and the fact that these four random variables are couplings, are a coupling of these four random variables means that this pair, S sub 1, S sub 2 with superscript 1, is distributed exactly as this pair. The second pair here in the second row is distributed exactly as this pair. But in addition, now they are jointly distributed because this pair and this pair in the original system, they do not have joint distribution, right? We agreed upon that in the beginning of the talk. But now I'm saying take the first pair and the second pair or their probabilistic copies and make them jointly distributed. And now you can ask the question, among all possible joint distributions that you can impose on this system, is there at least one in which the differences between the random variables are the same as when they are taken in isolation? In other words, the probabilities with which they differ remain the same in the context as they were outside the context, right? And this leads us to the general definition that, you know, if this happens, in other words, if I can find a coupling like this, then it means that the difference between the random variables when taken in isolation is the same as when they are taken within their context. And so there is no contextuality, even though I remind you, there is a context dependence in the sense that, you know, the probabilities change here from one context to another context. But there is no contextuality in the sense that, you know, adding the other elements of the context do not change these, you know, the degree with which the two random variables are different. I hope it is clear. If it is not, you can jump in and ask me questions, okay? And here is a kind of demonstration of the same thing on an arbitrary system. So what I'm doing, if I'm interested in this system and I want to investigate its contextuality, I will look at all possible couplings of this system. And I will, and this coupling obviously will respect all within context distributions. So for example, these three will be distributed in exactly the same way, as these three, right? And so on for each of the rows. But these rows here in the original system are all stochastically unrelated to each other. Now they are all jointly distributed. And I'm looking at all possible joint distributions subject to the following constraint, that these two random variables differ from each other with smallest possible probability. These two differ from each other with smallest possible probability. These two are differ from each other with smallest possible. So for any pair of random variables that are within the same, that have the same subscript, so they are sharing a content, they are answering the same question. For every pair of such random variables, I am minimizing the probability with which they are different from each other. And if I can't find this overall joint distribution subject to this constraint, then the system is non-contextual. Otherwise, it is contextual. And this would be a general definition, right? Then, so we have a system is non-contextual if it has a coupling in which any two random variables sharing a content or answering the same question coincide with the maximal possible probability. Well, which means that differ from minimal possible probability. If no such coupling exists, the system is contextual. And here is that intuition that I already mentioned too. The contexts are forcing the variables to be more dissimilar than they are when they are taken in isolation, right? So this is this meaning of contextuality that is the focus of contextuality analysis. Well, once you have agreed on the definition of contextuality, then the next question is, can I measure the degree of contextuality? How much contextuality is in a system? And it turns out that it is possible. For example, if you take this system that we have just considered, it is the cyclic system of rank 2. So let's say the two questions asked in two different orders, right? Then if you fix the individual distributions of these four random variables, then the system is described by these two quantities. One of them is the expected value of the product within the first row, and the second is the expected value of the product in the second row, right? So expected value of this product, expected value of this product will characterize the system if we fix the marginal distributions that are kind of, in this case, are not informative. So if you do that, then you get a box, and within that box, you get a polytope. And this polytope contains all non-contextual systems. So if your actual system is somewhere outside this polytope, it is contextual, and you can take some distance from this point representing your system to this polytope and take it as a measure of contextuality. C and T here stands for measure of contextuality. Index 2 refers to the fact that it is the second among three measures of contextuality that I and my colleagues proposed for measuring contextuality. So CNT2 is just one measure of contextuality. Well, this distance, as you see from the graph, is not the Euclidean distance, it is L1 distance. And it is, in this case, is a measure of choice, distance of choice, because it turns out that it is the same in all directions, right? You can go vertical or horizontally, or in other direction if if we have more random variables. And you will always, go the same distance and before you hit the surface of the polytope. Well, here it is for cyclic system of rank 3. So you have a three-dimensional thing, and you have this point outside, and each of the coordinate distances is the same, and it is a natural measure of contextuality here. It can be also analytically presented. I will not comment on the formula; it doesn't matter. But just to let you know that it's a well-investigated area in which we have not only not only computational procedures using linear programming and things like that, but rather we also have quite a bit of analytic results, quite a few of analytic results that actually describe systems, at least systems of a special form. Like in this case, it is about cyclic systems. So what's interesting about this this measure that I've just discussed, that it also can be used to measure the degree of non-contextuality. So if your system is within the polytope, then you can go some distance until you reach the surface of the polytope from inside, right? And this would be a natural measure of non-contextuality. So it's kind of interesting too. And here we also have various forms of it and some analytic results that I'm not going to discuss in detail. So just to give you the idea that it is an area in which we are investigating not only the classification of systems into contextual and non-contextual, but also measuring the degree of contextuality and non-contextuality. What might be of interest to you is that in certain types of systems, with certain measures of contextuality, it has been already shown that the degree of contextuality in the system describing, for example, a computer is, describing a quantum computer is proportional, or better to say, is monotonically related to the so-called quantum advantage of quantum computers over conventional computers. So if you, the more contextuality you have in this computer, the greater this quantum advantage that you gain. And this was shown relatively recently by my colleague Samson Abramsky of Oxford University, that there is a monotonic relation between the two, right? So it's contextuality, therefore, is not just of an academic interest, but it can also have these practical applications like that. And there are other practical applications that I will not get into. So let me now get to something that I thought might be more interesting to people who are in logic, or at least whose work is related to formal logic in some way. What if a system is deterministic? Well, deterministic system is just a special case of a system of random variables in which each random variable attains certain value with probability 1, right? So you have something like this. It is specific values of random variables, and they are attained with probability 1, but otherwise it is just a system of random variables. What can we say about that? Well, as it turns out, that there is a simple theorem that we proved several years ago that every deterministic system is non-contextual. So it is actually, in the case of a deterministic system, contextuality in that special sense of contextuality that I've just mentioned is not possible. Consider this situation with propositions. Let's say you have logical sentences from Q1 through Q5, and you can assign a truth value to each of these statements, right? So you will have various truth values assigned, and it is possible, or at least in this example, I allow for the possibility that the truth value is context dependent. So in other words, for example, this statement here is true in this context, but false in this context. Well, you probably know many examples of this happening. For example, if I say, my name is Ehtibar, and this context is defined by all sentences that are uttered by me, then it's a true statement. And in the other in the other context, it may be uttered by Damir, and in this case, the statement, my name is Ehtibar, is false, right? So depending on the context, the truth value of the statement can change. However, the system is not contextual in the sense in which I have just explained it. In other words, you can always there is always a trivial coupling of this system, such that the probability, if you wish, you know, 1 or 0 with which these two things are equal or not equal to each other remains exactly the same as when they are taken in isolation. So contexts do not add anything to that, to the difference between the two things taken in isolation. So this in a sense, you know, it tells us, well, it's no longer interesting. So let's return to random variables proper and work there, and nothing interesting can happen here. However, it is not exactly the case. Consider, for example, the well-known liar's paradox, right? So here there are two statements or two claims, and Nico's claim is that Zora's claim is true. Zora's claim is that Nico's claim is false, right? So it is well-known two-sentence version of liar's paradox, right? And you obviously you can also increase this you know, number of sentences. You can have three claimants, and they would say, you know, Nico would say Zora's claim is true. Zora will say Max's claim is true, but Max would say that the Nico's claim is false, right? So the last one should claim falsity, and the previous ones claim that the next claim is true. This is kind of the four-sentence version, and I could continue, but at this point I'm running out of my grandchildren. So, you know, I'm going to stop here. And in fact, I'm going to return to the three-sentence version just as kind of representative of all such systems, right? So let's say you have a system like this. So you know that it's a deterministic system in the sense that the truth value of a sentence is not a random variable. It is either true or false. However, you do not know which of the possible deterministic systems this system represents. Like, for example, in this deterministic system represents one possible variant of this system, right? So the pairs of statements that in which one statement claims that the other statement is true, they are perfectly correlated in the sense, in this case, they are always equal. So it's 1, 1 here, 1, 1 here. But in the last row, they should always be different, right? Perfectly anti-correlated. So 1, negative 1. But it can also be like this, right? The false statement, false and false, false and true, right? So if you count the number of possible systems that satisfy this constraint, that the two values within each of the first two rows are the same, and in the last row they are different, then there are 8 such systems, and they are all shown here. Now, which of them represents this system? Obviously, we have no preference. And here, these epistemic or Bayesian probabilities come into play. I simply say, well, since I do not know which of them, let me assume that they are all intermixed, kind of epistemically, not in the sense of kind of random variables occurring or not occurring in physical sense of the word. But I'm simply saying, since I do not know, I will assume that each of them can be representative of the system here with equal epistemic probability or Bayesian probability. And in this way, I will obtain so-called epistemic random variables. So this is a random variable that after you mix them, each of these random variables will be a binary random variable which is uniformly distributed with probability 1/2, 1/2. And you will have actually a consistently connected system, because this distribution is exactly the same as this distribution, and this is true here, and it is true also in this column. It is a consistently connected system. It's very simple, probably one of the simplest that you can imagine, but it is a highly contextual system, and the degree of contextuality here is the highest among all possible systems of this format, right? So if you consider any other system, its contextuality will be lower. Well, here I show only particular measure of contextuality that is my favorite at the moment, but it doesn't matter. For any system of any reasonable measure of contextuality will produce maximal contextuality here. So as you see, it is possible to consider at least some logical paradoxes in terms of contextuality, and by means of transferring them into epistemic random variables to measure the degree of contextuality in them. And, you know, those, at least some of these paradoxes produce very high levels of contextuality, which may kind of correspond to the degree of puzzlement that people experience when they encounter these logical paradoxes, right? With kind of psychological aspect of that. Well, I am not going to dwell on this, but we have also investigated various impossible figures. Well, I will discuss it in a bit of detail. This MC Escher's ascending descending lithograph. So what you have here is four flights of stairs, right? And you see that, you know, you can go up and up and up and up and return to the same position, right? Or you go down and down and down and down, also return to the same position. This creates this paradoxical situation. It's impossible to go up and up and up and up and end up where you have started, right? And so this creates this paradoxical situation, and we can formalize it by looking at exactly the same thing as before, namely that you have pairs of flights of stairs. So you consider, let's say this is 1 and this is 2. So I will put them together, 2 and 3. I will put them together, 3 and 4, and so on. So I have the cyclic system of rank 4. And essentially, you know, the relationship between this, the consecutive flights of stairs is that if along one of them you can go up on the next one, right? So they are perfectly correlated in all four. And we introduced the fifth one, which is a global constraints, which actually essentially something that should reflect our idea of how the system of flights of stairs can be constructed to make sense. So let's look at it in greater detail. So we again, for the first four, we have a cyclic system of rank 4, which is consistently connected and the simplest. So nothing strange about this one. But what can we say about this global arrangement of the four flights of stairs? Well, what we can say is that in general, of course, there are 16 possible combinations of up and down, right, for these four. So it is all these 16 are shown here. Plus means that you go up and minus means that you go down. However, if you move up or down and then end up in the same place where you from which you started, then the only possibilities are these 6, right? When the number of up stairs would be the same as the number of downstairs, right? So it means that you can go twice up and twice down and end up in the same place, or in any other combination, but it should be the same number. So there are only 6 possible combinations, and if you multiply them by the 16 possible combinations for here, we have 16 times 6, which is what, 96, I believe, possible deterministic systems. You assign the same probability to all of them, mix them up, and you will get a contextual system which has a certain value of contextuality, right? So again, kind of the strangeness of this Escher's picture is being reflected in a high level of contextuality that you get to find that, right? These are Penrose's figures, and here I indeed will not get in detail because it's kind of technical. You know, we have to classify these bars or edges of these figures in a special way, which we have done with my former student, Victor Cervantes, recently. And we have quantified each and every of such figures, and we have analyzed them contextually and found out that indeed the degree of strangeness of the figure corresponds to the degree of contextuality that we compute, right? Or if you wish, degree of impossibility of the figure corresponds to the degree of contextuality. So this is more or less what I wanted to talk about Now, Damir, how am I doing in terms of time? Tell me, is it time to finish, or do I have more time for?
I think 5 more minutes is fine.
Okay, it is a bit entertaining, so that's why with some hesitation, I will mention this. You know, these are very prominent gentlemen. You know, John Conway died relatively recently, and all of you probably know, a brilliant mathematician. Simon Cochin is actually the first person who introduced the notion of contextuality, and there is a very famous Cochin-Specker theorem, which is the central theorem in the theory of contextuality. So the two of them joined their forces in order to address the following question. You know, in quantum physics, if you have a particle and you are measuring a spin of this particle, let's say, right, and it can be up or down. The traditional view, the classic kind of the standard view in quantum physics is that it is fundamentally stochastic process. So in other words, there is no way, whatever you know about, you know, the circumstances or whatever, there is no way in which you can predict whether the measurement will end up in up or down, right, of a given spin. Now, if you are outside quantum physics, you can kind of challenge it, and you can say, well, what if actually they are predetermined in some way? But there are so many different circumstances here that, you know, some of the particles exhibit, you know, spin up and some of them down. You are pulling across huge number of particles, and therefore you get this determinist, this quasi-probabilistic stochastic behavior, right? And they addressed it in their so-called free will theorem, in which they claimed that they can prove that even from outside the quantum physics, you know, you can claim that the particles have the fundamental indeterminism, fundamental probabilistic behavior, which they, in a flashy way, they are putting, you know, in terms of free will. So they have free will, you know, of their own, those particles, right? And there is a particular formulation of this. Okay, I really do not want to tax your patience. And so what I'm going to tell you just this, that actually their proof is extremely controversial, in the sense that lots of people find kind of problems with their proof, including myself, right? Just this proof mathematically is challengeable. Let me put it very diplomatically. And it turns out that actually the same thing can be proved very, very, very cleanly and kind of simply if you consider the problem exactly in the terms, in the sense in which I have just presented to you these mixtures of deterministic systems. So essentially, their problem is this: that they have a probabilistic system, and they are asking the question whether it can be presented as a mixture of deterministic systems, right? Probabilistic mixture of deterministic systems, each deterministic system representing a particular particle, but, you know, they being different deterministic systems. So this is essentially the problem that they are attacking, right? And the key to the solution of this problem is that when you have a deterministic system and you are considering a specific form of system in which, like that EPR bomb system, in which there is no interaction between the two particles is possible, then each of the deterministic systems has to be consistently connected, like here. But it cannot be like this, right? And then, you know, the question becomes, if you have a mixture of consistently connected deterministic systems, can you obtain systems that we observe? And specifically any kind of contextual system. And it turns out that there is this very simple theorem that says that, it's impossible. So in other words, it is indeed what they claim. So it is the proof of their theorem. But this proof actually is like 2-3 lines long. It is very simple proof, almost by definition true, if you only consider the problem in these terms, the mixture of deterministic systems giving you an observed system. Right. So this is more or less what I wanted to mention. Since it will be recorded, I also put some literature here, for anyone who is interested to look at. This is the literature that covers the material that I mentioned in this talk, and that is all for my talk today. Thank you.
Thanks very much. So I can clap on behalf of the audience. Thanks. So I know a few people had to run, but we can take questions. Wit just took off, but posted a question. I don't know what to do with that. If you want to answer it or answer it later and by message or something, but if maybe we should go to other folks first if there are other questions.
Okay.
Anybody have any questions they want to go? I think just unmute yourselves.
Yeah. So maybe can I ask a question real quick?
Sure.
So it seemed like, especially at the beginning of your talk, I had the impression that the contextuality analysis was coming out of sort of applied problems. So coming out of applied problems sort of from physics about physical systems and how they can behave, or sort of with your one about the questions about traveling and the coronavirus, right? Out of some sort of social science analysis of people's attitudes or something like this. So when you do this type of analysis on a problem, so what is it that you are kind of getting out of it in the end when you discover that the system, say, has a high degree of contextuality or doesn't? I mean, does it sort of split along the lines that you gave at the end, where kind of deterministic things have very low contextuality or no contextuality, and things that are sort of impossible to paradoxical have very high? I mean, is this the sort of attitude that one should have about what comes out of this analysis?
Well, yeah. I mean, there are two ways of looking at it. One is to ask a pragmatic question. If you have your contextuality analysis kind of developed, and you are investigating different systems, what other interesting things in the systems the degree of contextuality or non-contextuality correspond to? And the example of answering this type of question might be that if you describe a quantum computer, then the degree of quantum advantage can be reflected in this degree of contextuality, right? Now, if you consider groups of people that are kind of communicating in some specified way, and you want to distinguish a group of people who are conspiratorial from the group of people who have not agreed on certain conspiratorial rules, before they started to communicate, the degree of contextuality, or in this case, non-contextuality, can be indicative of that, for example, right? So you can have some interesting things that are independently interesting, right? So quantum advantage, the degree of conspiracy and things like this, and you can correlate it with the degree of contextuality. So it is one aspect of this. And the second aspect, which kind of drives my interest in the area, is just that it is a fundamental property of the systems of random variables that we're discussing, right? So it is a way of investigating the nature of random variables and the most basic forms of stochastic relationships between random variables, right? So essentially we have a bunch of random variables, and we are simply asking the questions, what they measure or what questions they answer, and how they are combined together, right? And then you end up with very at least initial and not non-intuitive and rather puzzling phenomena, such that, for example, in principle, I could completely ignore the other person's measurements when I do my measurements. And so, my measurement is one uninterrupted set of realizations of a single random variable. But as soon as I take into account the measurements by another person, it turns out that the set of realizations that I have obtained in my experiment is being split into two: realizations of one random variable and realizations of another random variable. So it is, in a sense, it is puzzling. And every time when I give a talk for physicists, I always have at least one person who would be puzzled, well, unless they know it in advance already, who would be puzzled and say, well, but it means that there is some kind of interaction, right? That somehow the measurements of that other person influenced your measurements. If taking into account, those measurements will lead to this, right? And in fact, if you remember, at least you may know it from popular literature, that Albert Einstein famously was protesting against this type of analysis, saying that it is it indicates a spooky action at a distance, right? That is his famous expression attributed to him. Now, the point here is that there is no action, there is no interaction really here, but the nature of the random variable is relational. So random variable, the identity of the random variable is determined by all other random variables that are jointly distributed with this random variable, right? And it has very deep philosophical implications, in my opinion, and also it very nicely corresponds to Kolmogorov's theory of probability, when the random variables are defined as measurable functions on a domain space, right? So you have to know whether the random variables are on the same domain space or not. But in addition to what we can read in Kolmogorov's papers and books, you also have this possibility of relativizing it. So in other words, sometimes it depends on your point of view, whether you would place the things on the same random, same domain probability space or not, right? So there are many things here that can be brought up, and in my opinion, they are fundamentally interesting, just in their own right. But the applications, of course, is what mostly interests people outside this area, right? And in my opinion, right now, it is this quantum computer advantage is what is kind of the most hot area in the theory of contextuality.
Thanks.
Great. Other questions? So there is one person wrote in the chat. So please go ahead.
Okay. Can you hear me? Am I coming through fine?
Yeah.
Okay. Thank you. This was really fascinating. I had a question kind of about the impossible figures. So one of the things in philosophy I like to think about is dimensional ontology. And I was curious, so with these figures, if we confine them to a two-dimensional plane, then we obviously run into issues. But then are we allowed to treat like a higher dimensional context? So if we thought about these as sort of two-dimensional projections of a three-dimensional object, we can start to think about them as essentially like a Mobius or something like that. And if that is something that your work can also go into explaining and maybe be used to systematize aspects of dimensional ontology.
So first of all, yes, it is completely correct that if you are allowed to present them in as a projections of three-dimensional objects, then actually these three-dimensional objects can be constructed, right? And they have been de facto constructed for things like this. It's just that the three-dimensional object is not closed, right? So that the bars do not meet at a vertex. But if you look at it from a particular vantage point of view, you can see it the way it's written. So in that sense, they are not impossible. And when you analyze their kind of degree of impossibility or strangeness, you can adopt various ways of doing it. And one of them is actually getting into 3 dimensions and finding out how closely you can approximate the 3-dimensional thing with a 2-dimensional projection, right? Somehow, the kind of a normal triangle you simply can put on the sheet of paper, and that would be considered to be almost 2-dimensional, right? But this one you cannot. So it is possible to do it from this point of view, but our specific analysis here is actually based on a different type of encoding of the figures, right? So we looked at these edges, and you can see that you can have 2 types of edges. For example, this is type 1 edge, right? Where you draw these lines and both are visible. And this edge is type 2. One of them is visible and the second is hidden, right? And if you encode each of these bars by these edges, like for example, this bar would be 1, 0, and this bar will be 1, 0. This will be 1, 0. But here you have 1, 1 because both are visible, and so on and so forth. As it turns out that from this point of view, we are obtaining very simple representation of these figures by deterministic systems, and then when we mix them, we are getting this, quasi-probabilistic or epistemically probabilistic systems whose contextuality we can measure. So we are not specific. It is not a work in theory of perception or human perception. We are not really analyzing how we perceive these things. We are only analyzing how we could encode these figures so that, the degree of strangeness that we experience when we look at them can be somehow related to this degree of contextuality, right? So, but again, returning to your question about 3-dimensionality, 3-dimensionality is another way of encoding, but we tried it in addition to this encoding, and we simply did not succeed. So it was not as transparent as this encoding of the edges.
Okay, thank you.
Other questions?
So
I don't know if you had a chance to read Witt's question in the chat, or if you want to respond to it in the
can I see it when I share the screen? Probably not, right? I have to stop sharing.
Probably not. Yeah.
To stop sharing.
I can read it if you want.
Wait a second, let me.
So
I actually see the.
So the question was from Witt Tabor was, you speak of various values of contextuality, computing the maximal value for a given system, but what is the maximal value possible overall? Is there a bound across different systems? And what does it mean for one system to exceed another one in maximal contextuality, assuming this is possible?
Well, actually, it's a wonderful question. It is precisely the type of questions that we would normally investigate. So when you say that a system has a certain degree of contextuality, usually we are interested in maximal contextuality across systems having the same format. So it means that the same arrangement of random variables within the system, right? Let's say cyclic system of rank 3. And among all of these cyclic systems of rank 3, we can find one with maximal contextuality. And this maximum will be different than the maximum of contextuality for cyclic system of rank 4, and so on. Well, Having said that, it is true for the measure that I have demonstrated to you, this so-called CNT2, CNT2, the second of the three measures. The other measures, they have natural bounds. You know, you can propose measures such that the maximum degree of contextuality can only be 1, and minimal degree is 0. So all contextuality values are between 0 and 1. So such measures are also proposed. One of them is proposed by us, by me and my colleagues. In this case, you can also compare the degree of contextuality in let's say, cyclic system of rank 3 to degree of contextuality in cyclic system of rank 5, right? And say which of them is greater. But actually, we came to the conclusion recently. Well, I probably should take it back and say we are suspecting. We began suspecting recently that maybe it is not reasonable to have an overall bound for the measures of contextuality. So maybe it is actually better to have a degree of contextuality bounded for a given format only, and so that, you know, when you move from format to format, actually the comparison of the measures is not by simply taking one value and comparing to another value, but you can always, of course, take the value and another value and normalize them by the maximum for their formats, and then you will have a direct comparison, right? The forms of normalizations are also different, so you can have various forms of normalizations, and essentially. One of the problems that we often encounter in situations like this is not that we do not know how to do it, but there are too many ways of doing it. And we have to find one way that is principled way of doing it, which is better than other ways. So for now, for example, we do not know a principled way of doing normalization, right? So we simply leave it like as a contextuality measure for a given format. Right, but maybe in the future we will be able to come up with some ideas about how to do it better.
Great, yeah, thanks.